Okay, so let's quickly recap what we did last time. Last time we set up the scattering problem, right? And then we considered two cases. We always have in our mind the very simple picture that there is a finite region of space where the potential is non-zero, and then in vast regions of space the potential is indeed zero. So in the asymptotic past and asymptotic future, the wave function would look like e to the plus minus ikx, right? Which is a free particle wave function. And there is also a caveat here. We are not doing wave packet scattering. We are simply doing the simple-minded, non-normalizable wave functions because the answers to the reflection and transmission coefficients would turn out to be the same in both these pictures. So if you look at scattering from the left, our nomenclature was that any wave traveling to the right, we put a subscript r, right? And then e to the ikx represents a wave traveling to the right, with some velocity v. Of course, that only becomes apparent if you put the time dependence. But for now, for simplicity, let us simply say that e to the ikx is a wave traveling to the right, and e to the minus ikx is a wave traveling to the left. So in this case, in the scattering from the left example, our wave function will look like e to the ikx plus some small reflected portion of e to the e to the minus ikx, and a bunch of transmitted waves that look like t e to the ikx. Okay, and then we wrote down the conserved current in this case, and then argued that for current conservation, we should have the equation that the reflection coefficient plus the transmission coefficient should add up to unity, which is basically another way of claiming the probability is conserved. We repeated the calculation for scattering from the right, and then we argued that there must be some very simple relations between the reflection and transmission coefficients in these two cases. And we established what these relations are. Specifically, the transmission coefficient is the same, and the reflection coefficient differs at most by a phase. Okay, this is where we were. Okay. So today, let us take a concrete example, and I'm sure that this is all something that you guys have encountered in your studies on quantum mechanics before. So let us look at a very simple scattering problem and how do you approach it practically. And then if I have time, I will also set up what is called the scattering matrix. Okay, as a simple example, let us look at what is called the potential well. Sorry. So this is my v of x as a function of x, and the form of v of x is that for some finite region of space, there is a small well, and then it is zero pretty much everywhere else. So this depth of this well is minus v0. This is my x-axis. So between some point x is equal to minus a over 2 and plus a over 2, there is a small hole. Okay, this is a potential well example. Okay, so for this particular example, I want to set up the scattering problem and understand the scattering states. Okay, how do I set up the equation? First of all, before we set up the equation, so I'm assuming that I'm throwing some particle with some energy from the left. Okay, so if I'm throwing some particle from the left, my scattering example is my psi, which is a wave traveling to the right, should have the form. It is traveling to the right, so it's e to the ikx, and then it's going to look at this potential well, and some of it is going to be transmitted through this well, and part of it is going to be reflected. So the reflected part is r e to the minus ikx. This is a solution, asymptotic solution, and x going to minus infinity. In other words, this is the form of the wave function. If I solve the scattering problem, the form of this wave function should be e to the ikx plus r e to the minus ikx as I go sufficiently far away from x is equal to minus a over 2. And in the region x is equal to plus infinity, it is going to be some transmitted portion times e to the ikx. Okay, so this is the scattering from the left. So before we actually do this problem, remember that k. So what is k? K square is 2me over h bar square. So K is related to the energy, right? So if I throw the particle with a lot of energy, then I would expect that the potential will not have a lot of effect on this particle because it's going to just zip through the potential, no matter how what value V0 takes. Remember that in this V0 is greater than 0. Okay, it's a potential well. So no matter what the value of V0, if the K of the particle is large enough, it's going to zip through. So whatever answers you get, it should reflect this fact. If the energy is very, very small, then particle will not have enough energy to dig through the potential barrier and go to the other side. So all of it should be reflected back. So whatever solution you get, so this is understanding what is called limiting cases. In physics, this is actually a very important procedure. Even before you do the problem, it's useful to understand the limiting cases. So let us look at some extreme cases and try to figure out what your solution should look like. So in the limiting case, K goes to 0, my reflection coefficient should be 1. And in the case K goes to infinity, my transmission coefficient should be 1. My reflection should be 0. This is what I would sort of logically expect from the problem. Okay. So how do you actually do the problem? The way you typically the textbook set up this problem is by saying that there is 3 different solutions in 3 different regions. Of course, we have written down the solution in regions 1 and 3, right? So in regions 1 and 3, the solution looks like the first line of this guy and the second line of this guy. And what is the solution in region 2? Well, in region 2, I have to, oh, sorry, this is not showing up. So I'll have to stop share and reshare. Seems to be a very common problem. Okay. So in region 2, I'll have to solve the Schrodinger equation, right? How do I solve the Schrodinger equation? Well, here there is a potential, which is a constant potential of minus V0. So my Schrodinger equation reads psi double prime minus V0 psi equals E psi. Now V0 is just a constant, which is not x dependent. So this is still a simple harmonic solution. So minus h bar square over 2m psi double prime equals E psi plus V0 psi, or psi double prime is minus h bar square over 2m E minus h bar square over 2m V0 times psi. Okay. So I can write this as psi double prime equals minus k square plus V0 h bar square over h bar square over 2m.
So minus 2.
Sorry?
So there will be minus 2m by h bar square.
Sorry, there's 2m by h. Thank you. 2m over h bar square. So this term is incorrect. So this will be 2m v0 over h bar square. Yeah. So I can call this whole thing some other factor of q square. So this would simply be psi double prime is minus q square psi, which has a solution, of course, a e to the iqx plus b e to the minus iqx. Okay, so this wave has a slightly different energy because the total energy of the particle is now different. There is also a potential energy in this problem. Okay, so now the usual way to solve these problems, all problems of this kind, is to match the solution at the boundary. So you ensure that both the wave function and the first derivative of the wave function is continuous at the boundaries at x is equal to minus 2 and x is equal to minus a over 2 and x equals plus a over 2. Okay. Now it is important to match both the both the wave function and its derivative. The derivative matching is important because Schrodinger equation is a second order differential equation. So since it is a second order differential equation, we have to ensure that the second derivatives make sense. And if the second derivatives have to make sense, the first derivative better be continuous. So I will impose the condition that both the solution and the derivative of the solution is continuous at all the boundaries. So if you look at the boundary at x is equal to minus a over 2, I have to match this solution, which I will call equation 2, with this solution, which I will call equation 1, as applied to the x is equal to minus infinity case, right? So the x is equal to minus infinity case is e to the ikx plus r e to the minus ikx. So psi r of x at minus a over 2 should be equal to this psi at minus a over 2, which tells me that e to the minus ika over 2 plus r e to the plus ika over 2 equals a e to the minus qa over 2 plus b e to the iqa over 2. Okay, let's call this equation 1. If the derivative has to match, I should take the derivative of this equation and then match it with the derivative of the equation number 2 at the boundary x is equal to minus a over 2. So if I do that, if I take the derivative, I pull out a factor of ik from the first equation. So this would be ik times e to the minus ik over 2 minus r e to the ika over 2 equals, sorry, I will erase these portions again. Okay. So this is going to pull out a factor of iq, a e to the minus iqa over 2 minus b e to the iqa over 2. This is going to be my equation number 2. Okay. Similarly, at x is equal to plus a over 2, you have to match the solution psi at plus a over 2 with the solution. So remember that in the far right, the equation, the solution looks like t e to the ikx. So this has to be t e to the ikx at plus a over 2. And then you have to psi prime at a over 2 should be equal to t times ik times e to the ikx at a over 2. So this will give you an equation which is called equation number 3, and which this will give you an equation which you call equation number 4. And then you now have 4 equations, and you actually have 4 unknowns. The 4 unknowns are A, B, and R and T. Okay. And now we don't care much about A and B. Our goal is to figure out R and T. So from these 4 equations, you figure out what small r and small t are. It is a little bit of a tedious algebra, but you can do it. So let me write down what the answer is. Or at least I'll write down the answer for R. R should be equal to, after all is said and done, we should write everything in terms of the momenta. Sine qa e to the minus ika divided by q square plus k square sine qa plus 2iqk cosine q. Okay, this should be your answer for the reflection coefficient. And similarly, you can also work out what the transmission coefficient. Of course, reflection coefficient small capital R is just modulus of this guy square. Okay? So this is again an exercise. Figure out R and T and check that R plus T equals 1. Okay. So please take this seriously and work out this example. We'll also revisit this example in a tutorial problem later. Okay. So let us first now pause and understand if our common sense analysis holds true. So if the energy of the incident particle is very, very high, okay, in other words, if k goes to infinity, then I expect the particle to just pass through without any problem, right? In other words, none of it should be reflected back. Now, if you look at the equation for q square equals k square plus 2mv0 over h bar square. But in the limit that k is very, very large compared to 2mv0 over h bar square, q square is approximately equal to k square. So in this approximation, k square minus q square goes to 0, which implies that the reflection coefficient goes to 0. So the transmission coefficient becomes 1 because the square of both of these guys should be 1. Okay. So this is the first limiting case that we can inspect. The other limiting case is k goes to 0, which means you are throwing it very, very, very softly. So it just doesn't have enough energy to penetrate the potential barrier. So in this case, I expect all of the particle to be all of the waves to be reflected back and none of it to be transmitted. So if I look at the k goes to 0 limit of this equation, you would actually be able to prove that this is R actually goes to 0 in this limit. Okay. So if you don't believe me, so let us actually put k equal to 0 in the above equation. So R goes to minus q square sine qa, and e to the ika becomes 1 divided by q square. Sorry, the limit k goes to 0, R, I expect the transmission coefficient to be 1. This is minus q square sine qa, which is minus 1. And since capital R is mod of this guy's square, capital R will become 1 in this limit of very, very low energy of incident particle. Okay. So typically, you would have solutions for this particular problem, which are scattering states, which are perfectly valid scattering states. Of course, how much of the wave is scattered, how much of the wave is reflected depends on the energy of the incident particle. That is the first lesson. The second lesson is that in region 2 also the Schrodinger equation does have solutions, which means this solution can also admit bound states. So if the energy of the particle is such that it gets trapped in this potential and cannot escape from x is equal to minus a over 2 or plus a over 2, you could also have bound states of the particle. Bound states meaning you can have normalizable solutions to the Schrodinger equation, and these bound states can be actually worked out explicitly. Okay, so a given potential in one-dimensional or three-dimensional quantum mechanical systems can admit in general both bound states and scattering states. Of course, there are certain potentials that just don't have any bound states, and certain potentials that just don't have any scattering states. For example, simple harmonic oscillator has only bound states. Okay, and you cannot have a large enough energy such that the particle scatters off. But you can certainly have potentials of this form that admit both bound states and non-normalizable states, so to speak. Okay. So, the way you evaluate the scattering and reflection coefficients is by simply matching the solutions various boundaries and figuring out the normalization conditions. Notice that even though I set up the equations fairly easily, so solving this is actually a little bit of algebra, but if you just be patient, you would be able to figure out what small r and small t are for this problem. Okay. Similarly, I encourage you, even though I will not force you, to solve the same problem looking at scattering from the right. So instead of throwing the particle from the left, in which case my solution is e to the ikx plus r e to the minus ikx of this form, we can also look at scattering from the right. Okay, if I throw a particle from the right, then the solution inside the well remains the same, but since now the particle is traveling to the left, this guy would have a form e to the minus ikx plus r prime e to the ikx at x goes to plus infinity, and you would have some transmission e to the minus ikx as x goes to minus infinity. Okay, so we can also match this solution with the solution in the region number 2 to figure out what the reflection and transmission coefficients are. And if you actually do this, you'd be able to prove that the transmission and reflection coefficients in these two cases is related by these very simple expressions. Okay. Is this clear? Are there any questions? I'm sure many of you have seen this before.
Hello, sir.
Yes.
Sir, I have a question.
Yes.
Sir, when we are considering the scattering problem, all we are doing is throwing a particle through a potential. The wave function of the particle is transmitting through the potential or reflecting back, right?
Hmm.
But sir, why the wave function is not deflecting in other direction?
Why wave function is not reflecting in the other
Deflecting
direction?
in other direction?
Sorry, I don't understand. So what does that mean?
Sir, when I'm considering the classical mechanics,
Hmm.
when I'm throwing a particle in some potential, it can deflect in any other direction instead of 0 or 180, right?
So first of all, I'm claiming that I'm only doing one-dimensional problems, right? So
But if I go higher dimension,
if I go higher dimension, then of course you will have to evaluate what is called the scattering amplitude. And in 3 dimensions, which we will not do this semester, but next semester, the amplitude for scattering would be a function of both r and theta, as you point out. Okay, in 3 dimensions, there is 3 variables, r, theta, and phi. So in general, the scattering amplitude is a function of all 3 variables. But in cases where the potential has some spherical symmetry, it turns out if you have a spherical symmetry, it turns out that the phi part will not be present for reasons I will explain very carefully. And the scattering amplitude will be a function of both distance and angle. So in general, in 3 dimensions, you're absolutely correct. The scattering would be proportional. It won't be just reflected back as in 1D cases. In 1D is actually a very simple case of illustration. Of course, in the practical world, there is no typical 1D problems as such, with some caveats. For example, in condensed matter physics, there are linear chains of atoms in many metals that can be very well approximated to be a one-dimensional potential. So that is why these are very practical use, because you can actually model them as an approximate solution to many practical problems. But in general, you're absolutely right. The scattering would also have a theta part.
thank you, sir.
Any other questions?
No, sir.
Okay. Other questions from anyone else? Okay. So I will take about 10 minutes to set up something very interesting, which we will not have time to explore in great detail this semester, but it will be very useful for us next semester. And I will revisit this concept next semester also. This concept is called the notion of a scattering matrix. Okay. So in one dimension, the scattering matrix is trivial and can be easily written down in terms of these reflection and transmission coefficients. And it might seem to you that all we are doing is just changing the language, which is certainly true. But this actually takes a very important form in 3 dimensions when we do the actual formal scattering theory in next semester. So I want to give you a glimpse of what a scattering matrix is. Okay. So thus far we have written down the solutions to the Schrodinger equation as e to the ikx and e to the minus ikx. But notice that the way you interpret these e to the ikx is a little tricky. Okay, for example, if you look at this particular solution from the right solution, there is an e to the minus ikx in the solution, and there is an e to the r prime e to the ikx. So the first portion of this wave is one that is going towards the potential, and the second portion of this wave is something that is reflected back from the potential. So I can reformulate all of these guys by looking at things that are either going towards the scattering center or away from the scattering center. So I will draw a circle, okay? And this circle is supposed to represent the scattering center. So what is a scattering center? The scattering center is the non-zero finite region of space where the potential is non-zero. So this is the scattering center, where there is a non-zero potential. Okay. Now, suppose if I look at scattering from the left, I have, I'm throwing the particle in like this. Okay. So this is an incoming because it is going into the scattering potential. Now I can also throw the particle from the right. So this is also an incoming. Okay, I can also think of an incoming like this. So this is incoming, but since the wave is traveling to the right, this is incoming with sub r. This is also incoming. It is coming towards the scattering center, but since the wave is traveling from towards the left, I will write it as IL. Okay. Now, if I throw it from the left, the particle can also go to the right. Okay. And if I throw it from the right like this, the particle can be scattered to the left. Okay. So this I will call an outgoing wave, but since it is traveling to the right, I will call this as OR. This is also an outgoing wave because it is going away from the scattering center, but I will call this O sub L because it is traveling to the left. Okay. So instead of writing things in terms of e to the ikxs, I can write everything in terms of i's and o's. How will I write everything in terms of i's and o's? So I will write my psi r of x. I will write my psi r of x, psi l of x, reformulate in terms of incoming and outgoing waves. Okay. If I do it this way, I actually see a very nice, pretty form emerging. Okay. And this form will help us identify something called the scattering matrix. So I will write psi r and psi l in a slightly different way. So let us look at this psi l because it is right here. Psi l of x can be written as, so this is the case where I am scattering from the right. So e to the minus ikx part. So in this guy, so look at this piece by piece. The first piece is incoming from the left. It is this guy, right? Now, the second piece, which is r prime e to the ikx, refers to outgoing to the right, this guy. Does this make sense? If there is any questions, please ask. If I throw the wave from the right, it represents an ingoing wave traveling to the left, and the portion that is reflected represents an outgoing wave traveling to the right. And if you look at the t prime e to the ik, if you look at the t prime e to the minus ikx portion, that represents an outgoing wave traveling to the left. So it is this guy. Okay. So I may well reformulate this psi l of x as an incoming wave, but this incoming wave is traveling to the left plus a small coefficient r prime times an outgoing wave to the right. This is in the region x going to plus infinity, asymptotic past. Sorry, asymptotic solution in the region x is equal to plus infinity. And t prime, an outgoing wave to the left, OL, in the region x going to minus infinity. Okay. So I can reformulate my psi l of x in this particular fashion. So I will also write down psi r of x. Psi r of x, if I could remind you, is e to the ikx plus r e to the minus ikx in the region x going to minus infinity, and t e to the ikx in the region x going to plus infinity. But notice that since I am using outgoing and incoming, I no longer need to keep track of x is equal to plus infinity or minus infinity, because I know whether it's x is equal to plus infinity or minus infinity, because if I am looking at the solution for psi l of x, IL is always x is equal to minus infinity. Outgoing OR is also exactly the same way. So I don't have to keep track of it, but if you want, you can always keep writing it if you want. That is not a problem. So psi r of x in this language of incoming and outgoing radiation can be written as this is an incoming wave to the right plus a small reflected portion times an outgoing wave to the left, Similarly, t times outgoing wave to the right. So if you look at this, let us call this A and let us call this B. And if you look at A and B, they are all written, everything is written in terms of incoming wave to the left and outgoing wave to the left, and incoming wave to the right and outgoing wave to the right. So this invites us to use a matrix notation. So I can use a matrix notation and write down a column vector psi r, psi l equals, to a large portion, they are just IR and IL plus something times OR and OL. Okay. So what does this matrix formulation mean? Psi R can be written as, it's a relation between incoming radiation and outgoing radiation, basically. That is what this matrix equation represents. So if you look at equations A and equations B, we can easily figure out that psi R should be written as IR plus R times OL. So there has to be an R here, okay, and then a T here, and similarly, this should be an R prime and a T prime. If I write the matrix equation like this, you can easily check for yourself that it satisfies both equation A and equation B written above. Okay. This equation that connects the incoming and the outgoing waves in this particular fashion is a very important equation, and this matrix, which is a non-trivial part of the whole scattering, is called the scattering matrix. It's also called the S matrix. So notice that why am I writing it in this particular fashion? Because the solution, if the scattering is very, 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 very weak, then the particle is, if I throw a particle, is simply going to go without being affected by the scattering center that much. So the scattering matrix is basically T equals 0, R equals 0, R prime and T prime, everything is equal to 0. So psi R, psi L is simply the incoming radiation and outgoing radiation. So all non-trivial effects of scattering are encoded in this particular matrix, which is made up of the reflection and the transmission coefficients. Okay. So once I figure out what this matrix is, I know everything about the scattering problem. So the whole problem in the formal theory of scattering is to figure out the matrix elements of the S matrix. If I know the matrix elements of the S matrix, I know everything there is about the scattering problem. So I can write this matrix S as T, R, and R prime, T prime. Okay. And the matrix S has a very, very nice and important property. It is actually unitary. This is a unitary matrix. Now remember that it is simply made up of some components, which is all, they all have to be determined only after you give the potential, right? What is the potential? But there are certain properties of the S matrix that are completely general. They don't depend on the potential at all. And one of the properties is the fact that S is unitary. So if you don't believe me, let us calculate SS dagger. What is SS dagger? This is T, R, R prime, T prime times the dagger of this guy, which is T star, R prime star, R star, T prime star. So if I write this, I'll get 4 elements in general. The first element is mod T square plus mod R square. The second element is T, R prime star plus R, T prime star. The third element is R prime T star plus T prime R star. And the fourth element is R prime square plus T prime square. Okay. And since we have already established the relation that R plus T equals 1, which implies R mod R square plus mod T square is always equal to 1, you know that the diagonal elements is equal to 1. Okay. But what about the off diagonal elements? Well, from the off diagonal elements, we established a relation between the transmission and reflection coefficients from the left and the right in last lecture, which is this. T prime equals T and R prime is minus R star T over T star. So if you use the relation T prime equals T and R prime is minus R star, what was that? T over T star. you can actually prove that the off diagonal elements are equal to 0. Okay. So let us look at the 2, 1 element. What is r prime t star plus t prime r star? This is equal to minus r star t over t star times t star. And since t prime is equal to t, this is t r star, and this whole thing is equal to 0. So SS dagger equals 1001, which is actually quite remarkable if you think about it, because we did not actually solve for R and T, but based on certain general principles of what R and T should satisfy, this scattering matrix has the beautiful property that it is actually a unitary matrix, regardless of what potential you are talking about and what particular reflection and transmission coefficients you are talking about. But this remarkable property of the scattering matrix is simply a statement that you already know. This has to do with conservation of probability. Okay. So how this is related to the conservation of probability, we will actually demonstrate this in a simple tutorial problem by looking at it for a very simple solution and claiming that this SS dagger equal to 1 is simply an offshoot of the continuity equation. Okay, we will show this in the next class, but for now I will stop here. And if you have any questions, please do ask.
Sir,
Yes.
when we wrote psi L and psi R in terms of I and O's, then how were we able to get rid of x tends to infinity?